We're now going to look at the dependence of thermal conductivity on important parameters. So let's start with the dependence on n, where n is the number density. So if you substitute for the mean free path L, our previous result, 1 over square root 2, the number per volume multiplied by the total scattering cross-section sigma, our thermal conductivity, which was 1 over 3 and mean speed per particle, heat capacity per particle multiplied by the mean free path, becomes 1 over 3 nv bar c 1 over square root 2 n sigma. So you can see that these two n's will cancel each other, and at the end we will get a thermal conductivity kappa 1 over 3 square root 2 cv bar over sigma. So if n is doubled, you will see that the mean free path is halved. So kappa at the end is independent of n. So kappa is not a function of n. There is going to be one limit here that we should be careful about this n dependence. We will get to this later. Now, at a fixed temperature, we can look at the pressure dependence. Since we have for this dilute gas the ideal gas law, P bar is equal to nkt, the number density times Boltzmann constant times temperature, you can see that since it's independent of n, and if the temperature is fixed at a given temperature, we will have no dependence on pressure. Kappa is independent of the mean pressure P bar. So kappa is not a function of P bar. So that's what we find. And here is the remark we have to be careful about. So these two results are valid. These two results are valid when you have the mean free path much greater than the diameter of the molecules and much less than the container dimension L. So D is molecule diameter, L is container length, let's say, one dimension of the container. So this has to be the case. And remember, when we talked about viscosity previously, we found that the mean free path, it becomes close, well, it basically saturates at L when in the limit when we have a vacuum condition. So when the pressure is too low, you have the mean free path approaching the length of the container, in which case, since the L is a constant, it's not 1 over square root 2 n sigma, then you would have a dependence on pressure and n. So let's talk about temperature dependence. So for that, I would like to look at a monatomic gas in order to get a value for heat capacity per molecule. So for a monatomic gas, we had the mean total energy equals to 3 over 2 capital N KT, the number of molecules times Boltzmann constant times temperature. The mean energy per molecule is 3 over 2 KT, and the heat capacity per molecule, which is the mean energy per molecule derivative with respect to temperature, is 3 over 2 K per molecule. So normally this doesn't appear to be temperature dependent, so in a reasonable temperature range, reasonably higher than absolute zero, you will have 1 over 3 square root 2. For C, we will now substitute 3 over 2K, and then we have V bar over sigma. So these 3's will cancel, and we will get 1 over 2 square root 2 Boltzmann constant mean speed per molecule divided by the total scattering cross section. So that's not the end of the story for temperature dependence. On the other hand, we have V bar of the order t to the 1/2, so it has a t to the 1/2 dependence. Remember our approximation, V bar approximately equal to VRMS was square root 3 KT over M, so that comes from the equipartition theorem, and with this approximation we see that V bar is proportional to t to the 1/2, and C is usually T independent, as we have shown for a monatomic gas. So this gives kappa, the thermal conductivity should vary as t to the 1/2, but we have one more complication due to sigma, the total scattering cross section, where we have assumed hard spheres as our molecules. There is a sigma dependence on T. As temperature increases, sigma decreases, kappa actually increases more rapidly with T. So it's like T to the 0.7, if you remember. So let's substitute this V bar is equal to square root 3 KT over M to our kappa, where we would have 1 over 3 square root 2 C over sigma square root 3 KT over M, and you would get 1 over square root 6 C divided by total scattering cross section square root KT over M. Again, the temperature dependence comes from T to the 1/2 dependence of V bar, and also the total scattering cross section, which decreases with increasing temperature. Now, I want to make a comparison with viscosity. So kappa, our result for kappa is 1 over 3 and V bar C, the mean free path. And our result for viscosity was 1 over 3 and V bar M L. So if you take the ratio, the thermal conductivity of a gas to its viscosity, you have the following ratio: this heat capacity per molecule divided by the mass of one molecule. If I multiply this by Avogadro's number, then I would have the heat capacity of 1 mole of molecules, which is molar specific heat, and then Na times M is the molecular mass, the mass of 1 mole. So it is Cv over M. So kappa and the viscosity are related. So when we look at the ratio of molar specific heat at constant volume and the molecular weight of our gas, this ratio experimentally is actually slightly higher than expected. So we have a discrepancy with experiment. Basically, we're using a very not a very rigorous theory. So the discrepancy comes from the fact that we did not take into account any speed distribution and in the case of thermal conductivity, kappa, faster molecules will transport more energy. In the case of eta, the viscosity, faster molecules do not have any greater mean x component of the linear momentum on average. So we find that this ratio kappa over eta is experimentally somewhat larger than the ratio molar specific heat divided by the molecular weight. Okay, so we have analyzed the thermal conductivity of a dilute gas, and our results in our previous discussion was, our result was 1 over 3 and the number density V bar, mean speed per molecule, C heat capacity per molecule, L the mean free path. When we substitute for L 1 over square root 2 n sigma, we see an n cancellation, and so this suggests that kappa is independent of n, the number density or concentration of molecules. At a fixed temperature, P bar is directly proportional to n, so kappa is also independent of the mean pressure of the gas. But the remark is that the mean free path should be 1 over square root 2 n sigma. If the n is too small, if we approach the vacuum limit, the mean free path approaches L. In that case, L would saturate at the container length capital L, and you would have a dependence on P bar and M. So that's a detail for the limit of very low concentration and very low pressure. For the temperature dependence, if you substitute for the total mean energy 3 over 2 capital N kT, we find that the heat capacity per molecule is 3 over 2 Boltzmann constant. So when we substitute this here into the thermal conductivity, that doesn't contribute to any temperature dependence. However, V bar, which is approximated to be square root 3 kT over m, approximated to be equal to V RMS, which is actually not true if you remember the Maxwell distribution. So if we go back to our review of the Maxwell distribution, here you can see that V bar is actually square root 8 kT over m pi. V RMS is square root 3 kT over m, so we're basically neglecting the difference between these two and substituting for V bar, V RMS. So we find that by substituting square root 3 kT over m, we have a t to the 1/2 dependence of the thermal conductivity, but there is another complication because the hard sphere approximation for total scattering cross-section is actually not quite right, so there is a small temperature dependence. As temperature increases, the total scattering cross-section decreases, the thermal conductivity increases more rapidly with temperature. If you have a comparison with the viscosity, we can see that the viscosity is given by 1 over 3 nv bar ml instead of cl. So the ratio should be C over m, or molar specific heat divided by the molecular weight. And if we find that experimentally this ratio is slightly larger than Cv over mu, due to the fact that we did not take into account the speed distribution, the faster molecules will have a slightly higher rate of transport of energy, while the x component of the mean linear momentum does not change so much, so the effect on eta is negligible. So we find that kappa over eta is experimentally somewhat larger than Cv over mu.